30 years ago, a $20 bearing kit kept a motor running for decades. Today, median failure hits at 3.8 years, and replacement costs hundreds. That is not a defect. Manufacturers cut 45% of the copper, sealed the housings, and locked the firmware so no one outside their network can touch it. Your motor was designed to die, and what's keeping this repair scam alive goes deeper than you think. A Maytag service manual from 1975 spells it out in black and white. Service instructions said swap out the bearings, grease the shaft, and your washer motor is good for another decade. The part number for a replacement bearing kit, 872750, sat on the shelf for under $20. A routine job, done with a wrench and a tube of lithium grease, could keep a machine running for 30 or even 40 years. That was not a marketing fantasy. It was standard practice, confirmed by stacks of handwritten repair receipts and the memories of the people who did the work. One retired technician, Bob L., summed it up. He said, "We would drop the motor, swap the bearings, grease the shaft, and it would run another 20 years. The engineering behind that reliability was deliberate. Motors from the 1970s and the 80s used thick 14 or 16 gauge copper windings and high temperature insulation rated for 130 degrees Celsius. The housings were cast aluminum or steel, with removable end caps and access ports. Bearings were standard sizes, 6205 or 6000 series, readily available and interchangeable across brands. Even the wiring harnesses were modular, built to be unplugged and replaced without cutting a single wire. Service manuals called for bearing lubrication every 12 to 18 months and full bearing replacement every 30,000 to 40,000 cycles. That translates to 2 decades of average family laundry before a $20 kit was needed. Real world records back it up. Homeowners in the 1980s paid $24 to keep a Speed Queen spinning. Maytag's own warranty promised 10 years on the motor, with some commercial grade models advertising a lifetime tub and a decade of guaranteed motor service. In field tests, vintage washers ran fault-free for 35 years. The expectation across brands and across the country was that a motor would last as long as the house it was installed in, and that fixing it was a matter of routine, not a crisis. This was the baseline, the proof that durability was not just possible, it was the norm. Modern consumer motors are built on a different set of priorities. The teardown evidence is clear. Copper windings that once measured a solid 14 or 16 AWG have been swapped for strands as thin as 28 or even 30 AWG. That shift alone slashes copper mass by nearly 45%, according to teardown copper mass studies comparing motors from the 2010 era and the 2020 era. The result is more resistance, higher I²R losses, and a motor that runs hotter under the same load. In practice, what used to be a thick, low-resistance coil now heats up faster and sheds its insulating enamel years before the older designs ever would. The steel core has not escaped the cost-cutting knife either. Laminations that once measured 0.35 millimeters thick are now routinely stamped at 0.18 to 0.25 millimeters. Industry teardown reports and Department of Energy technical modeling both show these thinner stacks raise core losses by 12%, which translates directly into extra heat inside a sealed motor. That heat cannot escape because the old vented housings have been replaced by sealed injection molded shells. Those shells trap warmth, pushing the winding temperature even higher and accelerating breakdown. It is not just about numbers on a spec sheet. These material downgrades are deliberate trade-offs: less copper, less steel, and a housing that cannot breathe. Every shortcut compounds the thermal penalty. The engineering is not accidental. It is a calculated exchange. Longevity and serviceability are traded for lower production costs and a faster path to failure. The next time a modern washer or air conditioner motor dies after a few years, it is not bad luck. It is the direct outcome of design choices that prioritize disposability over durability. A repair shop email lands in the customer's inbox. It says, "We regret to inform you, your washer motor cannot be serviced. The replacement part is a sealed module and must be paired by firmware. Alongside the message sits a diagnostic screenshot, error code 734, flagged in red. The technician explains that the main controller refuses to recognize any part not on the manufacturer's whitelist. If a third-party bearing is installed, the software disables the motor entirely. The only solution offered is a full module swap, quoted at $398. No breakdown of parts, no labor line, just a single inflated price for a black box assembly. The invoice lists the module as sealed, no user serviceable parts inside. This isn't a one-off. Appliance forums fill with similar stories. Motors that could once be fixed with a $20 bearing kit now require a replacement that costs nearly $400, locked behind proprietary firmware. The lockout is not mechanical, it is digital. The controller checks the serial number, refuses to run with non-OEM parts, and bricks the motor if tampering is detected. The consumer, boxed in by software, faces a simple choice: pay up or throw out the machine. The repair economy has been rewritten, not by accident, but by design. Inside the lab, the breakdown sequence plays out with brutal clarity. When a modern sealed motor is pushed through an accelerated life test, 500 hours at 120 degrees Celsius, the first sign of trouble is a subtle but measurable rise in bearing drag. Polymer-filled bearings locked inside the stator lose their lubrication as heat and friction build. Torque readings climb steadily, with data logging a 40% increase in the force required to turn the shaft. This extra load doesn't just make the motor harder to spin, it pushes the windings to run hotter, raising the internal temperature by several degrees with each cycle. As the heat soaks into the copper, the thin enamel insulation begins to fail. Lab technicians measure a sharp drop in insulation resistance, falling below 10 megaohms after just 500 hours. Once the coating breaks down, current leaks between turns, causing localized arcing and carbon tracks. The winding resistance creeps up and the motor starts to lose efficiency. Meanwhile, the control board mounted directly onto the housing absorbs the same thermal stress. Solder joints crack. Thermistors drift out of specification. And the main driver MOS-VTs edge toward thermal runaway. The cascade is irreversible. A seized bearing forces even more current through the failing windings, which in turn accelerates heat damage to the control board. In test after test, the entire assembly collapses within weeks of the first bearing symptom. Once these design limits are crossed, there is no recovery, just a chain reaction that ends with a dead motor and a replacement bill that dwarfs the cost of a simple bearing fix. Service logs from repair technicians across the country reveal a pattern that is impossible to ignore. In air conditioning units, the most common failure is not the compressor or the fan, but the motor control board, a part that now carries a median replacement cost of $500 to $600. The logs show these boards rarely last beyond 3.8 years, with many failing just after the warranty expires. Washers tell a similar story. Inverter-driven motors, once expected to run for decades, now appear in repair tickets at the 4 to 5 year mark, almost always as sealed modules. The technician notes are blunt: no user serviceable parts, module swap only. For pool pumps, the numbers follow the same script. Service records list driver board failures as the top ticket item, with costs landing between $350 and $500. The median failure age hovers under 6 years. These are not isolated incidents. They span every major brand and appliance category. The data points stack up. A 3.8 year median for air conditioning boards, $400 for washer motors, $500 for pool pump electronics. The result is a repair economy built around high dollar replacements, not low cost fixes. These numbers drive home a simple truth: the short lifespan and steep repair bills are not random. They are the result of design choices that make repair the exception and replacement the rule. Sealed modules and proprietary electronics are not just technical quirks, they are profit engines. When a $20 bearing kit is replaced by a $400 sealed motor assembly, the math is simple. Manufacturers collect far more from each failure. Service margins on replacement modules routinely exceed 300% of the original part cost. Regulatory efficiency mandates, like a 15% reduction in kilowatt hours per cycle for washers and a 14 SEER minimum for air conditioners, give companies cover to redesign motors for compactness and integration. But these so-called improvements often come at the expense of repairability. The result is a repair economy where replacement is not just an option, it is the only path that pays. That is why sealed modules persist, even as costs for consumers soar. Not every brand has abandoned repairability. Speed Queen washers still use heavy copper windings and removable ball bearings, with motors that routinely cross the 25-year mark in service logs. Pentair and Hayward pool pumps offer cast iron housings and mechanical bearings that can be greased or swapped by any technician, with no proprietary firmware and no sealed modules. Even today, industrial rewind shops quote $1,450 to $1,650 for a full motor rebuild, restoring a failed unit to factory spec and giving it another decade or more of life. These examples prove longevity is a choice, not a relic. The blueprint for a 30-year motor is still out there, if you know what to look for. 3 checks can keep you from falling into the replacement trap. First, look for motors with removable bearing caps or listed bearing sizes. If you cannot find them, walk away. Next, demand a parts list and verify that replacement boards or bearings are available to the public. Finally, ask about software or firmware locks. If the manufacturer will not disclose repair procedures, you are buying into planned obsolescence. The next episode will expose more products built to fail and the few that still break the cycle. A $20 fix once bought 30 years of service. Now you pay $400 for a motor that dies in 5 years. This is not failure, it is design. As engineered obsolescence becomes the norm, every household pays the price. Next episode, the products built to break and the few that resist. Stay tuned.